All right. Welcome to Lab 8. Today we are going to be talking about binary trees, AVL trees, as well as tree traversals. As always, beginning with some announcements. Project 3 is due on March 28th at 11:09 p.m. If you don't already know, we are all conducting online office hours. Check the calendar schedule so you know when you can get help. As always, last week's lab is due this Friday, March 27th. Ensure that you submit the written problem to Gradescope because that's how we are doing handwritten problem right now. And Lab 8 is due on April 3rd at 11 to 9 p.m. And this time you're going to have both autograder and a quiz. All right. So we're going to be discussing last week's handwritten problem just as a refresher. The goal was given a sentence where you have different words and a prefixes vector where you have different words as well. You needed to replace each word in the sentence by the shortest prefix available in the prefixes vector. Before I go to common mistakes, let me just go through the solution. So essentially what you can see first of all is for to store prefixes, you're using a set and not an unordered map because all you need to have is access to those prefixes. You don't really care about the count. So that's a more efficient way of doing it. And that essentially takes about OMP time because you don't have an hour. So um, the second thing is the output, which is after you have replaced it by prefixes, what is it going to be? And then what you're going to be doing is you're going to be going through each word in the sentence because, of course, you had to find the minimum thing. And so that's going to take n iterations. You then are trying to find the right prefix to replace it by. And what you are doing over here is for each character of the word, you are sort of pushing back and you're trying to find the prefix because you need to find the smallest one. So, for example, if I'm trying to look at cattle, I'm first going to see, all right, does C exist in prefixes? No. Does CA exist in prefixes? No. Does CAT exist in prefixes? Yes. And therefore, you're going to be replacing it. And of course, since you're adding character by character, that's going to be the smallest prefix that's available in the prefixes set. So that's what you're doing. If you do not find a prefix, then you just break because that word remains the same. And that takes O of M time because each word has M letters. And then you're going to be pushing back the new prefix to the vector. So that's essentially the solution. You sort of see how you get PM plus NM square complexity. So some of the mistakes are, for example, using unordered map instead of unordered set. For prefixes, we just spoke about it. You not using a range-based constructor over here and making a new substring each time as opposed to just adding it character by character and so on and so forth. So do ensure that you go back and see this. And if you have any questions, go ahead and ask. So, like I said, this is the agenda of what we're going to be talking about. I have modified slides on this website. It's pretty much the same. It's just that if you want to follow along, um, these are just slightly modified so that I can teach better. And I'm also going to be doing a specific lab office hours tomorrow, which is 24th March from 3:30 to 5:30 p.m. Eastern Daylight Time. Here I'm probably going to just go through basic concepts, and if there are any interview questions that I can add, I'm going to be going through that. So if you need help with the handwritten problem or these concepts, I'm going to be doing this on 24th from 3:30 to 5:30. Okay, so let's start out with tree traversals. Um, but in order to talk about tree traversals, we need to talk about the different terminology. So as always, so let's just assume we have um, a tree. So I'm not going to write any numbers into them. So a root is a tree is a node with no parents. A leaf is a node with no children. As always, the internal node is as long as it has some children, and this includes root as well. I think depth and height are important to sort of distinguish. depth is the distance of a node from the root, and height is the distance of the root from the lowest leaf node. And siblings, so for example, this one and these two are siblings because they share the same parent node. So just as a warm-up question, let's sort of look at how you would potentially do this. So find the minimum depth of a binary tree, which is what is the depth of the shallowest leaf node. So an example of that would be something like, so if you have a tree like this, your minimum depth, these both are equal, is going to be 1. If you have a tree like this, then whatever is the minimum of the two, so your minimum depth is already going to be 1. However, if you have a tree like this, which looks like a stick, you will not, your minimum depth is going to be 2 because this one doesn't count. Take a minute, pause the video and try to work on this, and I'm going to be running through the solution in the next slide. Okay, so starting off with the solution, we can see that we are doing this minimum depth. Of course, if there is no root, you're going to return 0. If a left subtree doesn't exist, like we saw over here, then you're only going to be returning the minimum depth of the right hand side of right subtree. So it's like right subtree plus 1. 1 indicates this branch, this height of connecting root to the node. So you do a similar thing for the right hand subtree, and assuming you have a subtree that looks like this, where you have both left subtrees and right subtrees, you are going to be returning the minimum. You're going to be returning the minimum of the left tree and the right tree plus 1. Take some time to just think through this, and then let's talk about traversals. So there are 3 types of traversals that exist. One is pre-order, where you look at the node, followed by, so you're going to be saying this. So let's assume this is a tree, and I'm going to be making this a binary search tree. It doesn't have to be. So in this case, pre-order is going to be node left, right. So that's going to be 2, 1, and 3. In case of post order, you're going to be writing it in left, right, parent order, which in this particular tree's case is going to be 1, 3, 2. And in order is just, you're going to say left, followed by node, followed by right. And in this case, it's going to be 1, 2, and 3. Level order is slightly different from all of these. As the words indicate, you're going to be going level by level from left to right. So for this one, it's going to be 2, 1, 3. I just want to point out, this just so happens that pre-order and level order are the same. This doesn't have to be when it's in case of another tree. So one thing which you might wonder is, why do you need these 3 different kinds of traversals? How is it actually relevant? So this I found from a Stack Overflow post. So a way to think about pre-order thing is like, it's like a top-down recursion where you explore nodes first, followed by its leaves. You can think of post order as bottom-up recursion, where you're going to start out printing the leaves, followed by their corresponding parents. And with in order, if you go by in order, then you're going to be retrieving how it was originally inserted that resulted in information of that tree. So just as a, understanding how this might work in an actual setting. So what does this code essentially look like? Because we are trying to print it in these orders, correct? So one of the things that we saw was pre-order is essentially parent left, right? So you can see how the code for pre-order is, you're going to be visiting the head node, which is the parent node first. You're going to be traversing the left subtree, followed by traversing the right subtree. Now in order, again, you're going to say left, followed by parent, followed by right. and so on and so forth. So let's look at what pre-order traversal is. So just as a reminder, this is going to be PLR. So like we see, so it's going to be head left, head right. So let's do a quick example. If you have this particular tree, what would be the pre-order traversal of this tree? Again, pause for a bit, try it out, and then I'm going to be showing what the order is in the next slide. Right. So it's going to be this, and let's just quickly look at how it is, because you have parent left, right. So you start out, this is the parent, so you print 50. And then you're going to go to left. Now at left, again, you're going to be printing parent first, and that's why you're going to be printing 6. And then you again go to the left, you're going to say, this is the parent, so I print 4. It doesn't have a left child, so we ignore it. And then we have a right child, so you print 5. And you sort of go about doing the same way. So one way to think about these kinds of traversals is when you say parent left, right, you are going to be printing the parent first, followed by all like this order of the left subtree, followed by what the pre-order traversal of the right subtree. So when you're attempting this, it's good to sort of see, okay, is this the order in which my nodes tend to appear? So this is going to be great, where again for post-order traversal, you're going to do left, right, followed by parent. So we're going to take the same example. Why don't you solve what this will potentially look like? Okay, so again, we are saying this is left, right, and parent. So pretty much how we saw in the pre-order thing, this will see that you will print left subtree first, followed by the right subtree, followed by the parent. So you can see how 15 appears last. So just to quickly look at what this would go, right? So you come to 15, we are not the leftmost thing, so then you go left. Again, you go to 6, it doesn't matter, then I go left. But again, this still has children. So I'm going to say, all right, who is my left child? No one. Who is my right child? 5. So that is R. So you say R, and then you say, all right, the next one is my parent, because left, right, parent. And then you print P. And you're going to see a similar pattern over here, where before you print 6, you're going to print whatever the 4-5 order is, and then you're going to print 7. So just showing you a pattern of how this works. So in order, again, when you follow it, it's left node and left parent and right. So take the same example, take a minute, please solve it, and then come back to this video. Okay, so the same thing that I would repeat, you have left followed by parent, followed by right. So you can sort of see that over here, where you have left followed by parent, followed by right. So these 3 traversals are important. Let's talk about, how this would, so we spoke about these 3 different traversals. The next one is the level order traversal. So something that you have seen before in breadth first search, you are going to be looking at each level. And that's pretty much what you're doing here. And if you remember what you did with breadth first, you use the queue over there. And you're doing a similar thing over here. I'm just doing this. Just give me a quick second. I'm going to be locking this out so that I don't have to keep doing this right now. Okay. So we see a queue. You're going to be pushing the head. And then we see that we are going to say, all right, under the queue is empty. Pop this, print this, and then push the left one and then push the right node. So let's just take the same example we saw, or a different example, and just see how this would work. So in this particular example, so let's say we push head first. So we're going to be pushing 15. So this is in the queue. And we come over here, we say top is level Q dot top. I'm just writing my Q this way. And then I'm going to say, all right, we have stored top, so we're going to pop. So this is my printing place. So I print, and since this is popped, we are removing this from the queue. So once I've printed, I'm saying, all right, if I have a left child, then push my left child. So I'm going to be pushing 6. If I have a right child, then push my right child. So I'm going to be pushing 15. So just to do just like one more iteration, I push 6 over here, and then again, so since level Q is not empty because we have 6 and 15, I come back here. My top is currently 6. I pop it, and then I print 6. And again, I'm going to do the same thing where if there's a left child, I print 4. If there's a right child, I put 7 in here. So the other example where you did this is you did this in your first project where you had the stack in queue, and you can sort of see how that sort of thing is emerging. You can, oh, I'm sorry, this was supposed to be 23. That was totally my bad. So you can see how at each point, each level is being printed from left to right. And that's essentially your level order traversal. So again, now that we've seen this, this is sort of the easiest of the traversals. Take a minute and sort of write down what you think the level order traversal is going to be. Like we just ran through the example, you're sort of going 15, 6, 23, and so on and so forth. So given all of this, let's sort of look at, let's use level order traversal to see what happens. So in this case, you need to find, given a root to a binary tree, find the level of the tree which has the minimum sum. So again, we know what levels are. So this is level 1, this is level 2, this is level 3. So for level 1, the sum is 50. For level 2, the sum is 8. And for level 3, the sum is 117. And what you are going to be returning is the level at which you find the minimum sum. So take a few minutes. If you want to work with someone else online, go ahead and do that. And I'll explain the solution right in the next slide. Okay, so reminder, so we are saying the time complexity is O of n, which is looking through all of the nodes, and memory complexity on an average is going to be log n, otherwise it's going to be worst case O of n. This sort of comes with the type of tree because it's not guaranteed to be complete. You might just end up getting a stick tree, which is why you might get this kind of memory complexity. So looking at the solution, we know since you're doing level order traversal, you're going to be using a queue. At any point, you're only going to have the nodes at that particular level. And the reason for that is because at the end, you're just pushing the immediate left and right child. So here you take 15. So here you have pushed 15. So level size is currently 15 and my sum is 0. And of course, since I'm finding minimum sum, I'm going to set it to infinity so that whenever I do compare it, I am getting the right minimum sum and the right level. So we are seeing over here for the number of nodes that exist in the queue or the number of nodes that are on that level, just add the sum and then push the left and right thing. And something that you're going to notice here is since it's a binary tree, for each node that's on a level, so for example, for this node on this, since currently the queue has 6 and 2, I'm going to be pushing 30 and 80 and 7. So once you see that, we are storing minimum sum and the minimum level, and you return minimum level. So take a minute, pause potentially, and then just go through the solution to see if this makes sense to you. Okay, so that is the end of different tree traversals. Let's look at given traversals, how can you potentially deconstruct a tree? So we have these following traversals where we know that this is the in-order order and this is the post-order order. As a reminder, We know in order is L, P, R, and post order is L, R, P. So how do you know what this tree looks like? So just a recap to what we spoke about in traversal. Post order is left-right parent, which means the last node has to be the root node because that's as parent as it gets. So we're gonna start and we're gonna see. We're gonna put in your root as you know what your root is. Now the next thing is, so now that you know this is root and we know again that in order is LPR, when we determine that this is the root, we know this is its left subtree and this is its right subtree. And now we're going to use that to reconstruct this tree. So that's what we spoke about. So let's look at this, right? So we know 4825, this is the left subtree. And again, so this sort of allows us to know what nodes are there and then apply the post order traversal to this. So given that we know this is 4825, we know that this is the left subtree. And since post order is LRP again, you know the last node is the root of the left subtree. So then you put into over here. And you continue to do the same thing where you use the fact that you know this is LPR and this is LRP and continue to reconstruct this subtree by subtree. So you do that. So over here, 5 is to the right of 2. So you're going to put this 5 over here. We then come back. So we put this 5 over here and then we have the left subtree. So we have this 4 and we know 4 is at the end. So 4 has to be the root node of this subtree. And then we add 8. And you do a similar process over here. So you have 637 and you have 673. With post order, you know 3 is your root. So 3 is going to become 1's right node. Now we still have 2 more nodes left. Now in order, you already know it's LPR and therefore this is going to be the left node and this is going to be the right node. So just as a reminder, so always remember, like you need to use the fact that you know you have LPR or PLR or LRP and start off with the root. So for example, if this post order was actually pre-order, then I mean, we're going to ignore this, then 8 would have been your root node. So if you can do that and if you can sort of break through what this is going to work out, you should be able to reconstruct this tree. So I'm going to pause. So please, again, go through this, see what you understand, try to work out. I'll try and give some examples in some of the slides about like later about how other orders can work through. So that's essentially reconstructing a tree given the different traversals. Let's go a little bit into how this might work in a binary search tree. So you've seen binary search trees before, and essentially the property that it is going to be adhering to is that any node is greater than all of its nodes in its subtree, in its left subtree, and it is lesser than equal to all of the nodes in the right subtree. And we've seen again when we use binary search, it's easy to search if a particular item exists and insert it in the right place. So we see the insertion time for best case, worst case, and average case, and the lookup time are the same. So when do you hit these times? So the best case is when your root node is your root node is the node you're trying to like look for, or as the place you're going to be inserting. So then you're saying, all right, I'm going to say, actually, no, not inserting. So this is the lookup time. So I'm going to say 2. What is the worst case? Worst case is when you're in stick fashion. So at this point, lookup time is going to be O of n because you have to go all the way to find the node and then be able to insert it accordingly. With log n, let's assume it's a complete tree, then you're ideally just going to hit the height, or rather in this case, the depth of the tree. So then you end up getting lookup time of O of log of n. For insert, the worst case, the best case occurs when this is the place to insert, like you just know where the node to insert is, and then it kind of works out. Or let's assume you had no tree and you're just inserting the first part, then that becomes like a constant amount of time. And again, log n is when you go through the levels and you find a place to do this. All right. So we just spoke about it, where you start at root and traverse downwards until you figure where to apply, as long as it's adhering to the condition of a binary search tree. And deletion, I'm going to leave this for a bit and I'm going to show you through an example, and maybe we can come back to this. So in this case, we have an existing binary search tree, and we want to insert these following nodes to the binary search tree. So we're going to go through levels. So 3 is less than 8, 3 is less than 4, 4 doesn't have any children, so this is going to become its left child. We then just a second. All right, so I'm sorry for that. There was just a glitch with the button. Okay, so now we've inserted 3. Now we're going to do the same thing for 5. 5 is lesser than 8, or like, is it lesser than, greater than? It's lesser than. So I go to 4. Is 5 lesser than or greater than 8? Is greater than, sorry, if is 5 lesser than 4 or greater than 4? It's greater than 4. 4 doesn't have any right child, so you're going to insert 5 there. We now have 6. So you're going to do the same thing, compare at each level. At 5, it reaches a point where 5 doesn't have any right child, so you add 6 to it. 9, slightly different. You go to 8, you see 9 is greater. You go to 10, 9 is lesser. So then you add it as a left child. So this was fairly consistent. Let's look at how deletion works. So this is sort of similar to what you might potentially you may have seen similar things when we were doing max heap, except here you're ensuring that the binary search tree condition is kept. So over here, we're deleting the elements 5, 4, 8, 11. Now, when you delete 5, you are going to be replacing either by its in-order predecessor or its in-order successor. So in-order again is left parent, right? So left is its in-order predecessor and right is its in-order successor. Since 5 doesn't have any left child, we are just going to replace it by its right child. So at this point, it's going to be 6. Now, we need to replace 4. So you can take either of those things, because either of those things are valid because they are lesser than 8. So whether you put 3 as a root or 6 as a root, it doesn't matter. So here you can see the two different things where I have these both things. So now in this case, I am replacing 3 by, I'm replacing 4 by its in-order predecessor, and here I'm replacing 4 by its in-order successor. We now have to delete 8. And again, the same thing works. You're either going to be replacing it by its in-order predecessor or in-order successor. Why? Because right now we have in its left subtree, we have 3 and 6, right? If I replace it with 3, then I'm gonna break the binary search tree rule because 6 is bigger than 3. Therefore, 6 cannot be its left child. So if you traverse the tree, traverse the root, and you figure what its in-order predecessor is, when you replace it, the binary search tree condition is maintained. So that's why you see over here, I'm replacing 8 by its in-order predecessor, which is 6. And over here, I'm replacing 8 by its in-order successor, which is going to be 9. And if you see this tree, we still have the binary search tree condition maintained because you have 3 to the left, 9, 10, 11, or all of them are bigger than 6. 6 and 3 are to the left, 10 and 11 are to the left. So the whole subtree is lesser than the root. The whole right subtree is greater than the root, or greater than equal to the root. Now, deleting 11. So in this case, you either have I'm sorry, I'm just trying to figure out what this new tree is. So you have 3, 6, So right, so you have the same two trees where you have 11 over here, which needs to be deleted, and 11 over here, which needs to be deleted. Deleting 11 is not affecting any other part of the tree, so you just remove it. So now you have two valid trees. So something that you can see is both of these things are valid trees, except they were different, like you took different paths to get here. So you can have different validating valid trees, valid binary search trees. So we're going to be talking about what it means for it to be balanced or unbalanced, because right now, I mean, and why does it matter? So a balanced tree is where for every node K of P, the heights of the children differ at most by one. What does this mean in our previous example? So over here, this has this has one child, and this has like 0, like this tree is level 1, so the maximum difference is 1. In this case, again, the depth of this is 1, the depth of this is 2, and therefore the maximum difference between left and right is 1. And the reason for this keeping or why it needs to be maintained is when you have a balanced tree, you don't end up, encountering the stick-like scenarios where you might very easily end up getting O of n time complexity. So we can either balance it at certain points, or we can use AVL trees which have a specific condition because of which after every time you insert or delete, you can it automatically self-balances the tree. All right. I'm just quickly looking. Okay, so what is an AVL search tree? Just like I said, it's a self-balancing binary search tree. So it still has the properties of binary search tree, except it balances it out. And like we just said, it has these average and worst case of O of log n. So of course, efficient. So what are the invariants in addition to binary search tree? So again, this is a binary search tree invariant because of course it's a binary search tree. And then you have the balance factor, which is the height of the left subtree minus height of right subtree can only be in this range, like -1 or 0 or 1. So again, I'm just going to skip this description because the main part of this point is no matter whether you insert or delete, you are going to be rotating so that you maintain the -1, 0, 1 range. So let's look at a few examples. Now, there are 4 different cases that you typically encounter in an AVL rotation, and we're going to talk about a special case as well, but let's try to understand what this instinctively means. So over here, we can see that this one has height 3 and this one has height 1. Therefore, the difference is clearly greater than 1. So what is it that we do? We need to balance this out. So one thing which you will notice here is that the left subtree looks like a stick, and the goal is to change that. How do you change that? You're going to you have this +1 and the +2, you're going to go from bottom to top, and you're going to try and reverse that at the first point where you have an unbalanced tree. So you rotate right. So now you have 1, 2, and 3, and you have 4, 5. So you see how the binary search tree condition has been maintained, and now we have a balanced tree. Now let's look at the mirror image of this, right? Where you have a stick-like structure as its right subtree and not so in the left subtree. So you do the same thing. You are going to be taking this particular node and sort of rotating it left. Now again, same thing where you want to ensure that the binary search tree condition is maintained. So you just rotate this. This becomes a fair a balanced tree right now. Now, so one thing which you see over here is this is minus minus, and the reason for this minus minus is because over here the height of the left subtree is 0 because there is no subtree. The height of the right subtree is 1. So as we just saw in the beginning, the balance is left subtree height minus right subtree height. So this is -1. So if your right subtree is longer than the left subtree, then you're going to have minus values. If your left subtree is greater than the right subtree, you're going to have plus values. So let's look at a slightly different case. Over here, you have this kind of place where you have this one as a negative balance and you have this one as a positive balance. How do you go about doing this? One thing which so the whole goal of this is try to simplify it so that you can then get the right balance. So in this particular case, what you're going to do is you're going to convert this to the stick structure that we've seen before. And the way you do that is you rotate 1 and 2 and 1 and 3. And now we see that this is familiar because you saw this in the plus plus case. So you do exactly what you saw there and you rotate this at this point. So again, when you see something like this, where you have a plus first and then a minus next, you're going to make it into a stick structure and then do what you saw in the plus plus case. Similar to this, over here, you have minus as the top part and the plus as the bottom one. So you have differences. So similar to the left subtree, you're going to do the same thing over here, where you're going to make this into a right stick structure. This becomes similar to the minus minus case that we saw at the beginning. And then you rotate it, and now you have a balanced tree. So I would say just look at how this might work. We're going to see an example where it's not exactly the same. So let's look at this. You have -2 over here, you have -1 over here, but if you look at so -2 is clearly not valid. How do you go about changing this tree? One of the reasons you can't just do what this converting to a stick structure here is because you can see how these both are the same, but the problem is this one also has children, unlike the original case. So even if you try to make this into a stick structure, so you say 2, 3, 4, and 5, 6, that kind of simplistic structure changing at each level is not really going to work because the right subtree will always be bigger than the left subtree because there are so many different levels. What do you do instead? We're going to be thinking about in-order successor and in-order predecessor here. And again, we're still going to be thinking about stick structure. So what I'm going to do is I'm going to cut this part out because 3 is the in-order successor of 2, since I'm trying to balance out the right one. So once I do that, then what happens? Now I can just translate this into a balance tree where I just translate the stick structure to look like this. And now I can since 3 is lesser than 4, I can make 3 into my right child of the left child. Just because this is a slide, let me just go over this again. So we have this particular tree where the node that should move up has children. So this is going to be hard. How do we solve something like this? If the node 4 has to move up, then the 3 has to be to the left of that because 3 is smaller than 4. So what we do is we disconnect 3, we balance this out so that we now have this is 0 because this height is 2, this height is 2. And then since 3 is lesser than 4, we're going to make this the third child. So I think, so one of the things that you can see is because 4 was 2's right child and we changed it, it doesn't really matter because we now have a final child. But essentially, I think one thing which you should think about when you have complex tree structures like this is complex tree structures like this is to break away these nodes, because even if, so let's assume I had, I had something like 2.5 here and 3.5 here. The same thing sort of occurs where you will have, you'll rotate this becomes 1, 2, 4, and then you have 5 and 6. And since we are cutting this out, we are going to get 3, and then you say 2.5 and 3.5. So whatever is the in-order successor subtree, that's what's going to translate into the in-order predecessor subtree. This is a little confusing, so feel free to ask us questions about this in office hours. So given the situation, given that we understand these different traverses, these different balancing problems, let's look at a practice problem. So you have this particular tree. You are first going to be deleting the node 5, and then you're going to be deleting the node 7. And what would the resulting tree look like? And think about, we can assume that when we're replacing, we will always replace by the in-order successor. Pause this video, take a minute, solve this, and then we're going to attempt to solve this, and then we're going to come back and look at how that would work. Okay, so let's sort of do this step by step, right? So we know that we need to delete 5. If we need to delete 5, we need to replace it by its in-order successor 6. So we're going to delete this because this is not going to exist anymore, and we're going to make this 6. Right now, because this is an aerial tree, every time you delete or insert, you have to check for the whether any part of this is imbalanced, because every time you delete or insert, post that, it always needs to be balanced. So right now we can see that at this point, my balance factor is -1. For this, my balance factor is 0. For this, my balance factor is -1 because 1, 2, sorry, this is +1 because we have two two branches here and you have one branch here, so this is +1. Now we're going to do this side. So this part, because this is gone, this is 0. And we have this one node over here. So this is going to be -1. And then over here, we're going to take what the height of this is. So in this case, it's going to be 1, 2, 3, and then 1, 2. So this is going to be 1. We are overall balanced. Now, if we need to delete 7, what happens? 7 would again be replaced by its in-order successor 8. So let me just show what this would look like. Oh, great. So right now our current tree looks like this. We have 6, we have 3, we have 1 and 4 and 2. And over here we have 7 and we have 8. So now I'm going to be replacing 7 by 8. But what's happening over here? Like over here, we can see it's balanced. So this is -1. You have 2 minus 1. So this is +1. Over here, there is nothing. So this is 0. However, we have 1, 2, 3, and then 1. So this is +2. Therefore, this is not balanced anymore. So how are you going to modify this? Now, this is similar to the special case that we just saw. You can see over here that you have +1 and you have +1 and +2. So this is not going to be similar to the stick problem we've seen before. So let me draw this again for clarity. So we have 6, 3, 1, 2, 4, and 8, which is currently not balanced. Okay, that was not really, let's see. All right, so we can see that this one is not balanced. So what do you do instead? I'm just going to make this the same level. So remember, we have to cut it off. So right now, this is the problem because this one has two children. We are encountering, we can't make this into a stick structure. So I'm going to cut this off. And then what do I do? I'm going to make this into 1, 2, 3, 6, and 8. And then I'm going to rotate this around. So I'm going to be moving over here. So now my tree is going to be 1, 2, 3, 6, and 8. We did have a disconnected 4 node. So now that's going to go over here. So we can see that like this is one way of doing it, but since we had to replace it by in-order successor, we can see that we are getting over here where you have 1 and 2, and then you have 3. And since we disconnected 4, you get this particular structure. And we can see over here that this is now balanced. So just the step that I did differently over here was the fact that I took 1 and 2 and 3 and then I rotated it. I left it B. I didn't have to do anything over here because this was already balanced. So we just moved and we moved over here and we got this particular structure. So these are just practice problems, which I will talk about later, which I can talk about tomorrow. But that essentially marks the end of these different things that we've looked at. So you had KVL trees, you had binary search trees, and you had the different kinds of tree traverses. So I would say at the end of this, you should pause and write down the things that you had questions about so that, whenever you have officers, you can answer, you can ask for answers about these. So our handwritten problem today does use the current, the concepts that we've seen right now. So let's look at that. So the handwritten problem is saying, let's try to find the diameter of a tree. And in this case, the diameter of a tree is the maximum number of edges that can connect. So for example, over here, we have this particular branches of trees that mark the longest distance between one end of the node and the other end of the node. And you can see in all three examples, they are the very last node. Even in this case where you have almost a stick structure, since A does not have a left subtree, A becomes the last node. So you need to find what set of nodes are going to give you that particular, that value. So what you need to be doing is you need to be returning the diameter. You're being given this particular class. So do not modify anything in this class. You can see how you have a node and you have left and right children. Each of them have a value, and null pointer means an empty tree or a missing child. And we can see over here, so you have this diameter 8 because you have 1, 2, 3, 4, 5, 6, 7, 8. And if you take any other edges, for example, you take 1, 2, 3, 4, 5, that's lesser than 8. If you take F, C, G, so 1, 2, 3, 4, that's wrong. You can't do A, C, G, F, M because A is not the last node. You have to look at what its last node is, which either doesn't have any subtrees or it has a missing child. So thank you so much. And again, if you have questions, please go ahead and ask. Just as a reminder, I'm going to be doing my lab 8, the concepts that were covered over here from 3:30 to 5:30 p.m. tomorrow, which is 24th March Eastern Daylight Time. This is the Zoom link, and this is on the calendar as well. And this marks the end of lab 8.